Hello everyone. I hope all of you are doing well and staying safe. I'm going to look at a problem on moments about an axis. Okay, so let's start off with a problem. Here's a problem. And there will be some parts of this problem where I'll solve using the scalar approach and the other part using the vector approach. Okay, so first of all, I have the following figure. There is a door that is held open about the xy plane. Okay, so here is the situation. So I have the z-axis. Okay, then I have the x-axis, which I have drawn here, and then I have the y-axis. I'm going to take the y-axis and extend it onto the other side as well because I need it. So here is the y-axis extended onto the other side. Let me just make sure that this is parallel to what I have here so that I can now draw it as a dotted line. Okay, so I'm going to take this, bring that guy here, and then this is going to be a dotted line. Okay, now so this is the xy and the z axes. So this is z, okay, this is x, and then this is the y direction. Now what I have is I have a door that is held open by means of a cable. Okay, and here is the door. I'm going to draw the door in a second here. Okay, so this door has a certain length along the x-axis, and it is held at an angle with respect to the y-axis. So here is how it's going to look like. I'm going to copy that and paste that here, and then I'm going to take that and then I'm going to paste that right here, and then let me increase the size of these lines a little bit, okay, so that it looks like I guess I didn't mean to do that. I want to do this one. Let's hope that it looks like an actual door. Okay, so it's going to be this way, and similarly on there. Okay, so this is a door, and let's say that this door is called as OCAD. Okay, let me make sure that these lines are drawn this way. So starting with the origin of the coordinate frame, so this is going to be the point O. Okay, then this is going to be the point C, and then I'm going to have the point D here, and then I'm going to have the point A, which I'm writing down here. Okay, so this is the edge A of the door. So this is the edge C, this is the edge A, then this is the point D, and then I'm given some dimensions, and before I do that, I have a cable that is running from the point A all the way to a point B. Okay, so here is the situation. So here is the point A, and then here is the point B. Okay, so that's point B, and obviously if I have a cable, then the cable is going to be in a state of tension, so there is actually a force that is acting along the length of this cable. Okay, and this force is given as having a particular magnitude of 200 newtons. Okay, so this is a force F. Okay, and then F has a magnitude of 200 newtons. Okay, so given that F has a magnitude of 200 newtons, and of course the axis, I'm going to draw this x-axis as the hinge axis. Okay, so there is a set of hinges that are placed on the x-axis, as you can see here. Okay, so this is one set of hinge, and then this is the other one. So there are some hinges that are placed on here. Okay, and so that the door can be raised up and down with respect to the x-axis, and dimensions of the situation are as follows. Okay, so first thing is I'm going to draw a line parallel to the y-axis all the way from here. Okay, and then I'm going to drop a perpendicular on here, and I'm going to start copying some of these things. So I'm going to copy that, and I'm going to paste that right here. Okay, and let me do the following. Let me take this line and then join it with respect to that. Okay, and so now I'm going to do them all in terms of dotted lines. Oops. So this is going to be a dotted line because these are all dimensions that I'm talking about, and likewise this is also going to be some kind of a dotted line here. Okay, and let me say that this line here, which I'll just bring all the way down here, this is also a dotted line. Okay, now here is what I'm told. This angle by which the door is held open is given to me as 15 degrees. Okay, so this angle here is given to me as 15 degrees, and the length from point O to point C is given to me as 1 meter. which obviously means that the length from point O to point A is also going to be 1 meter, or point D to point A is also going to be 1 meter, because it's the same door that we're talking about. The total length of this door along the x-axis is given to me as 2.5 meters. So this distance is known to me as 2.5 meters. And since I know the hypotenuse here, obviously the angle in there between OC and the y-axis is also 15 degrees, right? So this distance here, I'm going to call this distance here, and then I'm going to have one more distance here. Okay, so this is going to be 1 times cosine 15, so many meters. Okay, and then the height distance here, which I have written, this I'm going to say is 1 times sine 15, so many meters. This is the same as this. Okay, 1 times sine 15, so many meters. Okay, and the location of the point B. Okay, so this point B is raised up by a height of 1 meter above the z-axis, and it's at a distance of 0.5 meters away from the z-axis on the x direction. Okay, and let's see, so here are the dimensions. It's a point on the xz plane, so maybe it might help us to draw the xz plane if possible. So let me do that very quickly. Okay, so if I draw the xz plane, draw a line parallel to the x-axis, let me take some of these details and then bring them out here. Let me take this guy and maybe reduce the length of that guy, and let me now bring this down here. Okay, and let me make these all dotted lines. The key thing is in all these problems is to get these figures properly done. Once you have the figures properly done, right, then the rest is just easy. Okay, now here is a dimension that I'm given in this problem. Distance from point B all the way along the x-axis. Okay, so this is a distance of 0.5 meters. And then the height of point B from the x-axis is a distance of 1 meter. Of course, not drawn to scale, as you can very obviously see. Okay. So the x-axis is also called as the hinge axis. Okay, so because that is where the hinges are present, as you can see. Okay, so let me mark that out. So this x-axis is also the hinge axis. Okay, where the hinges are present, which are drawn in this blue color, as you can see. Okay, so I hope the problem is clear to all of you in terms of how the drawing is done. Okay, so this is the information that is given to me in terms of the magnitude of the force. Okay, all right, what are the things I need to do in this problem? First thing, obtain the moment of the force about the hinge axis. Okay, let me use the vector approach first. Okay, vector approach, and then I'll also use a scalar approach. Okay, and then the next thing I need to do is obtain the moment of the force about a line joining the points C and the point D. Okay, that's let me use the vector approach for that. Of course, you can use the scalar approach too, but let me do it using the vector approach. Okay, just to get ourselves familiar. And then lastly, obtain the moment of force about a line joining let me write this properly, joining the points C and B. Okay, that's the other thing. Okay, so I have all of these that are to be done. Okay, and we need to do both the vector and the scalar approaches, which is perfectly fine. But first, let me do the vector approach. Okay, and typically to do the vector approach, and even for the scalar approach, I need to write the force as a vector, and I immediately recognize that, okay, hey, the unit vector along the line of action of the force is directed from point A to point B. Okay, so the unit vector along the line of action of the force is U A B. Okay, so here is typically what I do. I will take this figure once again, and I will keep making use of this figure. I'll clean up this figure a little bit, okay, for my own sake. But then let us start off the problem doing the following. Okay, first one, moment about the hinge axis using the vector approach. Okay, so to do this, I write the force as a vector. Okay, so the force has to be written as a vector. So that's my first step. Write the force as a vector. Okay, let me come back here and then paste this figure once again so that I have this figure for reference. And to write the force as a vector, I need the coordinates of the different points. So I need the coordinates of point A. Okay, so as you can see, the coordinates of point A, these can be easily written, and here are the coordinates of these points. Okay, so A is at a distance of 2.5 meters from the positive x direction. So let me scoot this up and write it out a little closer so that I have enough space. So this is going to be 2.5. Okay, then along the y-axis and the z-axis, it's a distance of 1 cosine 15, and then a distance of 1 sine 15, so many meters. And then the coordinates of the point B. Okay, what are the coordinates of the point B? Now B is at a distance of 0.5 meters along the x-axis. It's on the xy plane, and then a distance of 1 meter along the y-axis. Okay, so if I have these two, then all I have to do is the following. I'll get rid of this pesky line here. Okay, then I come back here and I say, okay, my force F is force times the unit vector along the line of action of the force. This is going to be force times the position vector by the magnitude of the position vector. Okay, and so I can write the force as the following. So F is equal to the magnitude, which was 200, times the position vector, coordinates of the last point minus the first point. So this is going to be 0.5 minus 2.5i, and then it's going to be 0 minus 1 times cosine 15j, and then it's going to be 1 minus 1 times sine 15 in the k direction, and all of this will be divided by the square root of the sum of the squares of these quantities. Okay, so I'm just going to write this very quickly. So this is going to be in a sense 0.5 minus 2.5 is minus 2, so that's going to be 2 square, and then this is going to be 1 times cosine 15 whole square, and then this is 1 minus 1 times sine 15 whole square whole to the power 1 by 2. So if I do this, okay, which you have here, I will end up getting the force as a Cartesian vector. Okay, very basic ideas once again. And so the force can be written as the following. It's going to be minus 141.8i minus 68.8j plus 123.4k, so many newtons. Okay, so this is the force written as a vector. That was a little darker blue than I needed, but anyway, this is good enough for me. And then what I do is the following. Okay, I go to my next step. Okay, so I started off by calling this a step 1. So my step 2, choose any point on the axis of interest. Okay, so we are interested in the hinge axis, which is the same as the x-axis. Okay, so I'm going to choose a point. on the x-axis. What are my choices? If I look at the figure which you are seeing very briefly here without the rest of it say shown to you, I can choose either point O or point D. Okay, so which means can choose either point O or point D. Okay, so I will choose, so let me choose point O. You can choose point D as well, there is no harm done. Okay, then what I do is this. Okay, then find the moment. Okay, so find the moment of the force F about the chosen point, which is the point O. And how do I do this? I do this using the cross product. Moment about the point O due to the force F. So what do I do for this? I go back to my figure. Okay, I have to do the cross product of the position vector and the force. Okay, so how do I do this? I can either go from RO to RA as a position vector, or I can go from RO to RB as a position vector. Let me get rid of this creature here, so I don't need that right now because we already are done with it. So I can either go from RO to RA, so I can go this way. Okay, so that's going to be the position vector. I'm going to write it out as ROA, or I can go from RO to RB. That is also a completely legitimate choice. Okay, it does not matter what I do. Either of them is fine. Okay, so I can say that the moment of this force about the point F is going to be either ROA crossed with F or ROB crossed with F. Okay, can choose either. Okay, so let me choose ROA cross F. Okay, so this is going to be the following determinant. So this is I, this is J, and then this is K. Then ROA, how do I write ROA? That is fairly straightforward because I have the coordinates of point A minus the coordinates of point O. So you can see that's quite silly. It's 2.5 and then cosine 15 and then sine 15. Okay, so this is going to be 2.5 and then 1 times cosine 15, 1 times sine 15. Okay, this is going to be the second row of the determinant. The third row is filled by the force 141.8 negative minus 63.8, and then lastly 123.4. I'm not going to evaluate the determinant. I know that you all know how to do this, and I have shown this in my videos as well, so I'm going to skip to the answer here. This is going to end up being 137.6i minus 345, sorry, that did not come out as a 4, so 345.4j. Okay, and then this is going to be minus 34.4k, so many Newton meters. That's my next step. This was step number 2. Then step 3, write out the unit vector about the axis of interest. Okay, axis or line of interest. So hinge axis, which means that U hinge is just going to be the unit vector along the x-axis, right? Because this is essentially what it was. And then what do? I take the dot product between MOF and U hinge, and that's going to give me the magnitude of the moment about the hinge. Okay, so this is going to give me, M hinge due to the force F, the magnitude only. Look at this. Okay, so this is going to be the dot product of this force with the unit vector. Okay, and so this is going to be the dot product of 137.6i, 345.4 j minus 34.4k, dotted with I, which is the hinge axis. Okay, which means that the moment about the hinge is going to be 137.6 Newton meters, and then express it as a vector, m hinge vector is equal to m hinge magnitude multiplied by u hinge, which is fairly easy, right? So m hinge is going to be 137.6 multiplied by the magnitude, multiplied by the unit vector, which is I, and this is so many Newton meters. And this is fantastic. So we are done. This is the Cartesian form. Here was the magnitude. Okay, couple of things that I want to underline. U hinge, which is the unit vector along the hinge axis. Okay, that was our previous step. And then we did the dot product between the moment that we found out and the hinge unit vector. Okay, that's something that we did as well. And we also had to choose any point on the axis of interest after writing the force as a vector. Okay, so this is the answer for the first part of the problem. While I'm doing the vector approach, let me also do the following. Okay, let me also try to find the moment about the line CD. Okay, so let me say, okay, this is B for me. Okay, so B, so use the vector approach to find moment about line joining C and D. Okay, so that's the second thing I'm going to be finding out. Okay, here are my steps. Write the force as a vector. This we have already done, right? Which means that this force vector is going to be the following. This was already done in the previous step, 141.8i minus 345.4j, and then 123.4k. This was so many newtons. Okay, then the second step. Okay, choose a point of interest, choose any point on the axis of interest or line of interest. So choose any point on the line or axis of interest. Let me write the line properly. Line or axis of interest. Okay, so let me go back to my figure. Okay, so here is my figure. I need a cleaner figure, so let me go back and pick up this creature here. Okay, and let me get rid of many of these things that you might be seeing in the figure. Okay, which is not necessary for us at this point in time. Okay, so let me say, okay, I'm going to get rid of I guess I don't need to get rid of too many things. This is good enough, I think. Okay, so choose any point on the line of interest. Okay, so what is the line of interest for us? So the line of interest for us is the line joining the point C and the point D. Okay, so this is the line of interest. Is the line from C to D. Okay, so I can choose any point on this line of interest. I can choose the point C or I can choose the point D. It does not make any difference to me whatsoever as to what I want to choose. Okay, but typically I can choose the point, let's say I choose the point C. Okay, so let me choose the point C. So choose point C or point D. Either choice is perfectly fine. Okay, so if I choose the point C, then what is my next step? I need to find the moment of the force F. Okay, this is going to be about the point C. Moment of force F about point C. Okay, and how do I do this? So this is just going to be M about C due to the force F is given by the cross product of the following. Okay, so now I can either go from point C to point A as a unit as a position vector, or I can go from point C to point B. So let me just go from point C to point A, or I could have just rather chosen point D to point A as well. That is also completely fine. It makes no difference to me. Okay, so let me go from point C to point A. So I need a good color for this, so let me choose the black color. Let me see if that works out. So from point C I choose a position vector that goes to point A. Okay, so this is going to be RCA, or I could also do RCB. That is also completely fine. Okay, maybe I could move this creature out of the way, and I could say, okay, I could go from RC all the way to RB as well. That is also completely fine. Okay, so this is going to be RCB. Okay, so a moment about C due to F is RCA crossed with F, or RCB crossed with F. Okay, and here is what I'm going to be doing. So a moment about C due to the force F. If I'm choosing the point A and the point C, and if I'm doing it as RCA, here is what I'm going to end up getting. So this is IJK, and then position vector RCA is the coordinates of A minus the coordinates of C. Right? It's very obvious to see that point C and point A are on the same elevation and on the same location in the y direction. So the only thing that's going to be left for me as I go from point C to point A is the distance of 2.5. So this is going to be 2.5i, 0j, and 0k. Okay, so that's essentially what it's going to be. Okay, and so this is going to be 2.5, and then 0, and then 0. And then I have the force, which is minus 141.8, and then this is minus 63.8, and then this is 123.4. Okay, so this is essentially what I end up getting, and it can be very well seen as to what this answer is going to be. Okay, so moment about C due to the force F is going to be I times essentially 0, and then I'm going to have minus j times 2.5 times 123.4. Okay, so this is going to be 2.5 times 123.4. Okay, and then I'm going to have plus k times 2.5 times minus 63.8. 2.5 times minus 63.8. Okay, so I unfortunately did not simplify this, so I'm just going to keep it this particular way. So this is going to be 0i minus 2.5 times 123.4j, and then this is going to be minus 2.5 times 63.8k. Okay, so this is so many Newton meters, I'm sorry. Then I come to the next step. Okay, step 4, choose the unit vector along the line of interest. Okay, so choose or write out the unit vector along the line of interest. Okay, this is going to be, the line of interest is CD, which means that the unit vector is going to be along the line CD, so which means that the unit vector UCD. Okay, so this is going to be the position vector divided by the magnitude of the position vector. Okay, so distance from C to D, I know the coordinates of C, I know the coordinates of D. Okay, so if you want very quickly, we can do this. The coordinates of C are 0, 1 cosine 15, 1 sine 15. The coordinates of D, D is just a point on the x-axis, so this is going to be 2.5, and then 0, and then 0. Okay, which means that UCD is going to end up being the following. So coordinates of the last point minus the first point. So this is going to be 2.5i minus 1 cosine 15j minus 1 sine 15k. All of this. And divided by the square root of the sum of the squares of 2.5 square, 1 cosine 15 square, 1 sine 15 square whole to the power 1 by 2. Okay, so this is going to be UCD. And then my next step is take the dot product of MC with respect to F and the unit vector UCD. Same procedure, I write the force as a vector, choose a point on the axis of interest, then I find the moment of the force upon the chosen point, then I write the unit vector along the line of interest, and then I take the dot product. Okay, so then this is going to give me MCD due to the force F. This is going to be MC due to the force F dot of the UCD. And I'm going to go to the next step, to write it as a Cartesian vector. MCD as a Cartesian vector is going to be the magnitude times the unit vector. Okay, and I actually have the answer. I have computed the answer. I know I'm skipping a couple of steps here in the pursuit of time. Okay, so this is going to give me MCD, okay, is 119.3 I. Please check my answers and let me know if there are any issues. 46.1 J minus 11.5 K, so many Newton meters. Okay, so this is the moment about the line CD. I guess these are not very straight lines today. Something is wrong. Okay, so this is how you write it as a Cartesian vector. So the previous step was finding it in the terms of its magnitude. Okay, so this gives you only the magnitude. But most times we also want it as a Cartesian vector, and this is typically how you write it as a Cartesian vector. I want to do one more thing, very last thing before I go and do the scalar approach for the first part of the problem. So I'm going to say, okay, part C, obtain moment about line joining C and B. Okay, now you got to be very careful. There are a couple of instances in which moments will be ending up to be zero. Okay, when can moments be zero? In the following situations. Okay, so notice. Okay, so this is important. Okay, so important. Okay, so in the following situation, moments can be zero. Moment about a line or an axis is zero. Okay, and what are the two situations? Okay, there are actually two situations that you can find out. Okay, the first thing is this. One is if the line of interest intersects the line of action of the force. Line of action of the force. Okay, that is one situation where the moment can be zero. The other situation where the moment can be zero is if the force is parallel to the line of interest. Okay, so if the line of interest intersects the line of action of the force, then the moment is zero. Okay, then moment is zero. And then if the force is parallel to the axis of interest, obviously if I apply a force parallel to a door, I cannot move the door anywhere, right? So this implies that the moment is zero. Okay, think about this intuitively. Okay, this is not just a mathematical construct. This is actually intuitively true. Okay, there is nothing that is artificial about these two statements in that sense. Okay, so which means that if I go back to my statement here, I'm asked to find moment about the line joining C and point B. But you see, point B is a point on the line of action of the force, right? Because I can go back here to my figure. You see, if I want to find the moment about a line joining C and B, the point B is a point on the line of action of the force, which means this force cannot produce any moment about that particular line. Okay, so that's what I'm going to be writing down here, and you can go back to my figure, of course, and take a look at it. Okay, so back to our problem. So when we look at line joining C and B, this line will intersect the line of action of the force. Okay, which means that line CB intersects line of action of the force, which means that the moment about CB due to the force F is 0I, 0J, and 0K. Okay, so this is something that you really want to pay close attention to in a problem. Suddenly you might be asked, okay, what is the moment about this particular line? Look at that problem carefully. If that is a line that is intersecting the line of action of the force, then you don't need to do anything. It is just 0. Okay, and then you can also check this by actually going through the procedure and then finding out that it is indeed 0. Okay, that's something that I want to write down, so you can also follow procedure above, follow the steps to find moment about a line outlined above. You will end up getting MCB to be 0. Okay, so this is mathematically true. This is also physically or intuitively true. Think of it once again. If I'm applying a force that is parallel to a door, I cannot move it. If I'm applying a force along a line, let's say that you want to open the door and the door is opened about the hinge axis. But then if I'm applying a force along the hinge, on the hinge axis itself, how am I going to be able to open the door? I cannot, right? Because I don't have any moment arm, or I don't have any lever arm. I don't have any advantage in doing so. Okay, so that is the reason why this is ending up 0. Okay, then I go back to the last part of the problem. Okay, to find moment about the hinge axis using let's say the scalar approach. Okay, so once again, I go back and bring my figure. Okay, so that's something I'm going to do very quickly. I want a cleaner figure, so I want to get rid of some of these details and so on. Okay, so look at this. I'm going to bring this guy, okay, this big guy here. I'm going to copy that and bring that down here. This is a long problem, right, because it has so many parts. And then here are the things that I'm going to be doing. I'm going to be getting rid of a lot of these things. Okay, so I'm going to cut that off. I don't need any of these things right there. I'm going to cut that off as well. I don't need any of those guys. I can cut that off. I don't know if I can. Yeah, I did. All right, that is successfully done. Okay, then I'm going to get rid of this force as well, because I'm going to cut off that, and I'm also going to cut off this this line here. I'm probably going to get rid of everything, as you can see. Okay, so I'm going to cut this off, and then all of these I'm going to get rid of it. Okay, we'll come back and write out some of these things if necessary. Okay, and likewise, so all I want is just the door. Okay, so I want to cut this off, cut that off, and cut that off as well. Okay, here is the hinge axis, so let's call that as the x-axis. So this is the hinge axis. Now I have a nice clean figure. Okay, then here is what I do. Well, I still can get rid of some of these things as well. Who needs them, right? Then what I do is this: bring out your force from earlier. Okay, so write out force F from earlier. Okay, and this force, as you can see, was having the following components: 141.8 I minus 63.8 J, and then 123.4 K. Okay, this was so many newtons. Okay, which essentially tells me that, okay, Fx, the x component of this force, is 141.8 Newton meters along negative x direction. Fy was 63.8 newtons, not Newton meters, I apologize. Okay, this is going to be along the negative y, and then Fz was 123.4 newtons along the positive z. So I'm going to draw each of these components. Okay, so look at this. So I'm going to take the components and draw them. So there is one component along the negative x direction, so that's kind of tricky to draw, but I hope you can all see this. Okay, so this is going to be Fx. Then I'm going to have a component along the negative y direction, so that's going to be this component which I'm going to be drawing here, which I'm going to call it as Fy. And then I'm going to have a component along the positive z direction, which I'm writing it as Fz right here. Okay, so this is going to be Fz. Okay, now look at the force Fx. The force Fx is parallel to the x-axis, so based on what we just discussed, this is not going to cause any moment about the x-axis. Okay, so something that I want to write down here. So force Fx is parallel to the hinge axis, which implies that the moment of this force about the hinge axis is going to be 0I, 0J, 0K. This is easy, right? So which means that, I don't even need to consider this force Fx. Okay, so that's the end of the story. Okay, I don't want to do that, of course, here. I don't want to make my picture look worse than it is. Okay, and then what I do is okay, look at Fz. Let's take Fz. I need to find the moment of this force about the hinge axis, which is the x-axis. So maybe let me do this very carefully. Let me take this picture and then redraw it each time I need it. Okay, so I'm going to copy this. We are done with the Fx, so I'm going to get rid of Fx. Okay, so Fx is gone, it's history. I'm going to cut this off. I'm going to cut that off as well. Not sure how to cut that off, but all right, there we go. I'm going to get rid of Fz as well. Okay, then I have a Fy. To find the moment of this force about the hinge axis, here is what I do. From the hinge axis, I draw a line parallel to the force. Okay, so let's say, maybe let me choose this color. So from the hinge axis, I draw a line parallel to that force. Okay, I take the line of action of this force and then I extend it. And then I can see immediately that, okay, hey, if I need the perpendicular distance between these two, then that's going to be this distance here, which I had already written at some point in time, right? Or it was this distance here, if I want to be a little more careful about doing it. Okay, so this angle was 15 degrees, that was 1 meter, so this is going to be 1 times sine 15, so many meters, which means that the moment about the hinge axis, okay, due to the force Fy, is going to be the magnitude of the moment, which is Fy times 1 times sine 15. And then if I use the right hand rule, fingers of my right hand aligned with the force Fy, my palm is facing the axis of interest. So your fingers are actually pointing, your palm is actually facing down on your paper or your iPad, okay, as you're doing this. Curl your fingers, your moment is going to be pointed along the positive x-axis. Okay, so which means that this is going to be the direction of the moment, okay, about the hinge axis due to the force Fy. So this is going to be a positive I. Okay, so that's one thing that we did. Okay, then I need to do one more thing, right? I need to find the moment about the hinge axis due to the force Fz. So let me copy my figure from before. So something has taken place here which I'm not too sure about, but let me see if that's because my iPad pen does not have much of a charge, and that's true. Okay, so let me just wait for a minute here. So what's typically going to happen is that if I scoot back to my figure here, if I look at Fz, right, all I have to do is find the perpendicular distance between Fz and the hinge axis, use the right hand rule, and I should be good to go. Okay, so let me see if my pen is ready and charged up. Probably should be, because these things charge up really quickly. So let me not copy this, let me copy this figure right here. Okay, and let me hope to God that I can finish this very quickly. Okay, so I'm going to be doing this one here, copy this figure, paste it out here. I'm done with fx, so I can get rid of all of that. I'm done with fy as well, I can get rid of that. I can get rid of this guy, I don't need that. To do this, with respect to the hinge axis, I draw a line parallel to the force Fz, and then I find out, okay, what is the perpendicular moment arm, or what is the perpendicular distance? Look at this. So if I take this and then if I extend this line down, okay, so look at this, extend this line down, I take the line of action, if I extend that down as well, what is the perpendicular distance going to be? The perpendicular distance, as you might have guessed, is going to be in this direction. Okay, so this is the perpendicular distance. This was an angle of 15 degrees, that was 1 meter, so this is going to be 1 times cosine 15. Okay, which means that moment about the hinge due to the force Fz is the magnitude Fz times 1 cosine 15. Direction, right hand rule, fingers of your right hand aligned with the force, your palm faces the line of interest or the axis of interest, curl your fingers, your thumb is going to be pointed along the positive x direction for this as well. Let me draw it in the red color as I've done before. So this is going to be this direction as well, and so this is M hinge due to the force Fz. Okay, so this is also going to be in the positive I direction, so many Newton meters, and then eventually I have to write out the resultant. Okay, so M hinge due to the force F is M hinge due to the force Fx, M hinge due to the force Fy, M hinge due to the force Fz, due to the force Fx, this was anyway 0, we found out. Okay, and this is just going to be the following. Let me go back to my darker color. So Fy times sine 15 was what we had, and Fy, if you look at the value, was 63.8. Okay, so this is going to be 63.8 times 1 sine 15 in the I, and then the other one is going to be 123.4 times 1 cosine 15 in the I direction as well, I'm sorry. So I can add them up together as vectors, which tells me that M hinge due to the force F. If I add these two up, I should hopefully get the same answer that I had in the previous situation, which is around 137.6 I Newton meters. Okay, and this is by using the scalar approach. Okay, and typically the basic idea was the same. All I have to do is product of the force times the perpendicular distance from the axis of interest to the line of action of the force. Okay, as you can see, this is a perpendicular distance right there, and likewise, I also had this as the perpendicular distance between these two axes. Okay, 1 sine 15, as you can see. Okay, so if you want, you can draw this as the perpendicular distance as well. Okay, all right, so I hope this problem was fairly relevant to all of you. We've already done things on moments about a point. Moments about an axis is just an extension of that idea. But the basic steps are very simple if you're doing the vector approach. Okay, here are the steps. First step is to write the force as a vector. Okay, so let me just take a look at one of our problems here. First step is write the force as a vector. Then the second step is choose any point on the line or axis of interest. Then find the moment of the force about that chosen point. Once you do that, write out the unit vector along the axis of interest. Okay, whatever your axis or line of interest is, write out the unit vector, and then take the dot product to find the magnitude of the moment about that particular line. Okay, but if you wanted to write it as a Cartesian vector, you have to take the magnitude and then you have to multiply it with the unit vector along the line of interest in order to get it as a Cartesian vector. And in the scalar approach, the idea is that if I want to write it out as a vector, it is force times perpendicular distance and then the right hand rule. And then very lastly, two key points that I want to mention here. If the line of interest and the line of action intersect each other, the moment is going to be zero. That's one thing. Then if a force is parallel to the line of interest, typically as we saw in the scalar case where fx was parallel to the hinge axis, so it did not cause any moment about that axis, in that situation also your moment is going to be zero. So when something intersects something else, moment is zero. When the force is parallel, the moment is zero. I really appreciate your patience. I hope all of you are doing well. Take care of yourselves. Bye bye.